Welcome to Systemic Stack. My name is Kabir Anand. This is episode 26 of the System Engineering series, and today we will explore service mesh fundamentals in a way that helps you prepare for system engineering interviews on this topic. Dealing with hundreds of microservices means you'll eventually hit a wall where manual networking fails. We are diving into how the control and data planes automate security and observability. Understanding these layers allow you to justify when a mesh is actually worth the complexity, which is a huge signal in design interviews. This lesson opens with the microservice chaos factor and how separating communication from application code creates a cleaner infrastructure layer. You'll understand the core architecture, specifically how the centralized control plane coordinates with the data plane's sidecar proxies to manage traffic locally. From there, we'll dive into the three pillars of mesh functionality. First is security, where we examine how mTLS provides identity and how authorization policies enforce access control. Second, we'll walk through traffic management, including dynamic routing, retries, and the circuit breaking patterns that stop cascading failures. Third, we cover unified observability through golden signal metrics, logs, and distributed tracing. We'll wrap up by looking at the critical trade-off between operational overhead and system control, which is exactly the kind of nuance interviewers look for when they ask when it's actually worth adopting a mesh. By the end, you'll be able to identify exactly when a service mesh becomes a necessary asset rather than just additional complexity. Let's set the stage with a real-world scenario you might encounter in a senior engineering interview. Imagine you're at a company that's just exploded from 10 microservices to 200. Suddenly, the simple way you handle retries, security, and logging isn't working anymore. It works fine when everyone's using the same language and library, but as teams diversify, your networking logic starts to fragment. This situation matters because it's where the limits of manual management are reached. You're facing inconsistent timeouts and blind spots in your monitoring that make debugging a nightmare. If you ignore this shift in scale, your primary failure mode will be a death by 1,000 cuts, where small network blips cause massive, unpredictable outages. Interviewers want to see that you recognize this inflection point, where the cost of managing communication in code becomes higher than the cost of implementing a mesh. It's about spotting the bottleneck before it brings the entire engineering organization to a standstill, and that's the context we're operating in today. At its heart, mastering service mesh fundamentals is about owning the infrastructure layer to ensure your distributed system is secure, observable, and fully controlled. It works by abstracting the network away from your business logic, providing a consistent way for services to talk to each other regardless of what language they are written in. What matters here is that it gives you a global knob to turn for security policies and traffic rules without ever touching a line of application code. In a technical interview, being able to articulate this separation of concerns shows a high level of architectural maturity. A common failure mode here is treating the mesh as just another library. If you don't respect it as a fundamental layer of your stack, you'll end up with leaky abstractions that confuse your developers. Think of this as the nervous system of your microservices. It's what allows the entire body of your application to coordinate effectively, and understanding its underlying mechanics is the first step towards building truly resilient enterprise-grade cloud environments. We have to talk about the microservice chaos factor because it's the primary driver for mesh adoption. As your service count grows into the hundreds, managing security and traffic manually within your code becomes completely unmanageable. It works well enough for a small team, but at scale, every team starts implementing retries and headers slightly differently. What matters here is that inconsistency leads to fragile systems where you can't guarantee how a request will behave as it hops through 10 different services. The failure mode here is a total loss of visibility. You'll have an error happening somewhere in a deep chain and you won't have the unified metrics to find it. In an interview, pointing out that manual management is error-prone and doesn't scale is a key observation. You are highlighting that the chaos isn't just about the number of services, but the lack of a standardized way to govern their interactions. This chaos is exactly what we are aiming to solve by shifting the responsibility from the developer to the platform. Defining the infrastructure layer is the first step in bringing order to that chaos. A service mesh works as a dedicated layer that sits right next to your applications, handling all service-to-service communication independently of the business logic. What matters here is that it creates a clear boundary. Developers focus on features while the platform handles the network. If you don't define this layer clearly, you end up with networking code scattered across every repository, which is a major failure mode for long-term maintainability. In an interview setting, you want to emphasize that this layer provides a uniform way to apply policies. Whether a service is written in Go, Java, or Python, the mesh treats them all the same way. The failure to treat networking as infrastructure leads to dependency hell, where you're constantly updating client libraries across dozens of teams just to change a timeout setting. By establishing this dedicated layer, we ensure that the network is a reliable, invisible utility rather than a constant source of friction for the engineering organization. Decoupled communication management is the superpower of a service mesh. It works by pulling complex networking logic like circuit breaking and retries out of the application code and moving it into the mesh. What matters here is that it allows your services to stay lean and focused on their actual jobs. Imagine the relief for a developer who no longer has to worry about implementing complex mTLS handshakes or sophisticated load balancing algorithms themselves. However, the failure mode you need to watch for is the added latency and resource overhead that comes with this decoupling. Every request now has to pass through an extra hop, and if your mesh isn't tuned correctly, that can add up. In an interview, it's crucial to acknowledge this trade-off. You're gaining developer velocity and operational consistency, but you're paying for it with a bit of extra CPU and millisecond delay. A strong candidate knows that decoupling isn't a free lunch. It's a calculated decision to trade some performance for a massive increase in system-wide reliability and manageability. The control plane is the centralized brain of the entire service mesh. It works by taking your high-level policies like service A can only talk to service B and translating them into specific configurations for all the proxies in the system. What matters here is that it gives you a single point of authority to manage the entire network's behavior. Without a centralized brain, you'd be back to manually configuring hundreds of individual endpoints, which is a recipe for disaster. Now, a critical failure mode to discuss in an interview is the availability of the control plane itself. If it goes down, your data plane proxies will usually keep running with their last known configuration, but you will be unable to push any new changes. This stale state can be dangerous if you need to quickly block a compromised service or change a routing rule during an incident. You've got to ensure the control plane is highly available and resilient, because while it's not in the direct path of every request, its absence freezes your ability to adapt to changes. Now, let's talk about the data plane, which is made up of sidecar proxies. These proxies work by running right alongside every single service instance, intercepting all the incoming and outgoing traffic. What matters here is that it's where the actual work of the mesh happens. Things like encryption, load balancing, and metrics collection are all executed right here at the edge. A major failure mode for the data plane is resource exhaustion. If your sidecar consumes too much memory or CPU, it can starve the actual application it's supposed to be helping. In an interview, you should mention that the sidecar pattern is what enables the mesh to be language agnostic, which is a huge architectural win. However, you also have to be aware of the sidecar sprawl problem. Managing the lifecycle of thousands of these proxies requires robust automation, or else you'll end up with version mismatches and inconsistent behavior across your cluster. The data plane is where the rubber meets the road, providing the local enforcement for the global policy set by the control plane. Mutual TLS or mTLS is how a service mesh handles identity and security. It works by requiring both the client and the server to present certificates to each other, ensuring that both ends of the conversation are authenticated and the traffic is encrypted. What matters here is that it moves us towards a zero-trust architecture, where we don't assume the internal network is safe. In an interview, you'll want to highlight that the mesh automates the issuance and rotation of these certificates, which is a massive task to do manually. The failure mode here is usually related to certificate expiration or a failure in the certificate authority within the control plane. If the automation fails and certificates aren't renewed, your services will suddenly stop trusting each other, leading to a complete system-wide outage. It's a high-impact failure that proves why robust monitoring of your mesh's health is non-negotiable. You're trading the simplicity of plain text communication for a much stronger security posture, but you're also taking on the responsibility of managing a complex, distributed identity system. Dynamic request routing gives you incredible control over how traffic flows through your system. It works by allowing the mesh to inspect things like HTTP headers or cookie data to decide exactly where to send a request. What matters here is that it's the foundation for modern deployment strategies like A/B testing or canary releases, where you might want to send only 5% of traffic to a new version of a service. A common failure mode is misconfiguring these routing rules, which can lead to traffic black holes or requests being sent to the wrong environment. In an interview, explaining how dynamic routing reduces the risk of new releases is a great way to show you value operational safety. You can shift traffic away from a failing version in seconds without having to redeploy any code. It's a powerful tool for maintaining high availability, but it requires clear visibility to ensure that your traffic is actually going where you think it is. Without that feedback loop, dynamic routing can quickly become a source of confusion during a complex rollout. Standardizing network resilience is much easier with automatic retries and timeouts. The mesh works by enforcing these rules at the proxy level, so every service gets a consistent safety net without developers having to write custom logic. What matters here is that it prevents one slow service from dragging down the entire system by holding onto connections for too long. However, there's a significant failure mode you must mention in an interview, the retry storm. If a downstream service is struggling and every upstream service starts retrying multiple times, you can actually amplify the failure and knock the service completely offline. That's why it's vital to combine retries with jitter and back-off strategies. The goal is to be resilient to transient blips without making a bad situation worse. When you're asked about this in a system design interview, always mention that while the mesh makes it easy to add retries, you have to be careful with the configuration to avoid accidentally DOSing your own infrastructure. It's about finding the balance between persistence and system-wide stability. Failover and circuit breaking are your last lines of defense against cascading failures. These work by having the mesh monitor the health of service instances and tripping a circuit breaker if failure rates exceed a certain threshold. What matters here is that it stops a failing service from being bombarded with requests, giving it a chance to recover while protecting the rest of the system. In an interview, emphasize that this is how you achieve graceful degradation. You'd rather return a controlled error than let the whole system hang. A failure mode to watch for is setting these thresholds too aggressively, which might eject faulty instances during a minor spike in latency, actually reducing your capacity when you need it most. Conversely, setting them too high makes them useless during a real crisis. Getting this right requires a deep understanding of your service's baseline performance. When you can explain the mechanics of how a mesh ejects an unhealthy pod from the load balancing pool, you're demonstrating the kind of operational thinking that top-tier companies are looking for. Unified metrics collection is one of the most immediate benefits of a service mesh. It works by having every sidecar proxy automatically record the four golden signals: latency, traffic, errors, and saturation. What matters here is that you get a consistent bird's-eye view of your entire system's health without having to ask developers to instrument every single endpoint manually. In an interview, highlight how this solves the missing metrics problem that often plagues large microservice architectures. A major failure mode here, however, is metric cardinality explosion. If you're not careful about how you label and store this data, the sheer volume of metrics from hundreds of proxies can overwhelm your monitoring system and lead to massive storage costs. You've got to find the right balance between granular detail and operational overhead. When you can talk about the importance of having a standardized dashboard for every service link, you're showing that you understand how observability is the key to maintaining complex distributed systems over the long haul. Standardized access logs provide a clear, consistent audit trail for every interaction in your mesh. It works by having the proxies generate logs in a uniform format, capturing details like source, destination, response code, and request duration. What matters here is that when you're debugging a cross-service issue, you don't want to spend time translating different log formats from 5 different teams. You want a single, coherent narrative of what happened. From an interview perspective, the failure mode to discuss is the sheer volume of logs and the resulting ingestion bottleneck. Logging every single request can be incredibly expensive and can even impact the performance of your logging pipeline. Strong candidates will talk about sampling strategies, only logging a percentage of successful requests while capturing all errors. This gives you the visibility you need for debugging and auditing without breaking the bank or slowing down the network. It's about being pragmatic with your data collection so that your logs remain a helpful tool rather than an unmanageable mountain of expensive noise. Distributed request tracing is what allows you to reconstruct the full path of a single request across many microservices. It works by having the mesh inject and propagate unique trace headers as a request moves through the system. What matters here is that in a complex environment, a single user action might touch 20 different services, and without tracing, you'd have no way to see where the slowness is actually coming from. In a technical interview, you need to point out a crucial failure mode: header propagation. While the mesh does the heavy lifting, the application code still has to pass those headers from the incoming request to any outgoing calls. If a developer forgets to do this, the trace is broken and you lose visibility. This is a common pitfall that proves that even with a mesh, you still need a baseline of cooperation from the application. Tracing is the only way to truly understand the performance bottlenecks in a distributed system, and mastering it is a hallmark of a senior system engineer. Security in a service mesh goes beyond encryption. It's about fine-grained access control. This works by applying authorization policies that specify exactly which services are allowed to call which APIs. What matters here is that it enforces the principle of least privilege at the network level, ensuring that even if a service is compromised, the attacker can't easily move laterally through your system. In an interview, you should mention that these policies are managed centrally but enforced locally by the sidecar proxies. A significant failure mode is misconfiguration, where a policy is too restrictive and accidentally blocks legitimate traffic, causing a production outage. You also have to consider the complexity of managing these policies as your system evolves. Without clear ownership and naming conventions, your security rules can become a tangled mess that nobody understands. The goal is to create a ring of protection around your APIs that is both robust and maintainable, giving you confidence that your data is only being accessed by the services that absolutely need it. One of the most important things for an interview is knowing when not to adopt a service mesh. It works best when you have a large, complex system, but the overhead is real. What matters here is that a mesh adds operational complexity, latency, and resource costs. If you only have 5 microservices, a mesh is almost certainly overkill. A massive failure mode in many organizations is resume-driven development, where teams adopt a mesh because it's trendy, only to find that it makes their simple system much harder to manage. In an interview, you'll score points by arguing that a mesh should only be introduced when the pain of managing communication manually exceeds the cost of running the mesh. You're showing that you're an architect who thinks about the bottom line and operational reality, not just the newest tech. Always weigh the benefits of observability and security against the increased cognitive load and infrastructure costs. The right time to adopt is when your chaos factor is actually preventing you from moving fast and staying reliable. So, we walked through how a service mesh effectively tames microservice chaos by decoupling communication from your application code. I mean, instead of baking retries and security into every individual service, you're using this dedicated infrastructure layer to handle it globally. Remember the two-part architecture? The control plane serves as your central brain for policy, while the data plane uses sidecar proxies to manage the actual traffic. This setup is what unlocks mTLS for identity and those advanced routing patterns like canary release. When you're in an interview, be ready to defend the operational trade-off. You're trading some complexity for massive wins in observability and governance. It's all about knowing when your scale makes a mesh necessary, rather than just an extra layer of overhead. That brings us to the finish line for service mesh basics. When you're in an interview, keep in mind that they aren't just testing your knowledge of sidecars. They want to see if you can justify the operational tax. You've got to weigh 3 key areas: unified metrics, standardized logging, and distributed tracing, against the risk of added latency and configuration bloat. A strong answer shows you know exactly when the overhead becomes worth the effort. So don't just jump into a mesh by default. Now, if you want to dive deeper, don't forget to subscribe for more architecture breakdowns. It's been great having you here. Good luck with your system design prep.